Hello and welcome to another presentation from me, Ollie Epsom. Today we are going to have part one of an introductory talk which is going to be looking at the propulsion systems of nuclear submarines. This is obviously, for very obvious reasons that I really shouldn't have to overstate, only going to contain unclassified information, and in this particular presentation most of the pictures are either from the internet or they're from some of my old notes that I've had kicking around. Now let's get started. Okay, so in this presentation we're going to cover the following. We'll look at the types and intentions of nuclear submarines. In other words, what they are for, why they exist, and why people are prepared to pay such an enormous amount of money to have them. We'll look at the characteristics of a nuclear submarine propulsion system, so what it must be able to do. We'll look at some of the different types of nuclear propulsion system that are available, and we'll look at the propulsion layout of a quote-unquote typical British, in this case, attack submarine. We'll also look in the most general terms at some of the available noise reducing features. Now, as I've done with my other lectures on Navy propulsion systems, this part one, is going to be fairly general and relatively straightforward. I'm not going to, for example, in this section, talk about how nuclear reactors work and how they're controlled. But fear not, because in future lectures, which will be part two, we will take a more in-depth look at PWR, that stands for pressurized water reactor, which we'll briefly touch on in this lecture. We'll look at the design of PWRs, we'll look at some of the fuel types and options that you have, and we will look at some of the operating characteristics and control systems that are required for pressurized water reactors. We will look, which is particularly important for submarines, at electricity supply and safety features, particularly, for example, how they are ensured to be reliable. We will look at primary, secondary and emergency propulsion in a little bit more detail than we're going to look at in this presentation. And we will do a quick overview of propulsors, of maneuvering surfaces and ballast tanks. Again, the slight issue with submarines is that all the systems are linked in a way that perhaps surface ships don't have to experience, because submarines need to move in 3 dimensions instead of just 2 dimensions, or even you could argue 1 dimension with a slight change in the vector as you do on a surface ship. This picture on the right is, as far as I can tell, the engine control room of a Royal Navy Swiftsure class submarine. Now, as shall become apparent, I'm not actually familiar with the control rooms of this particular type of submarine, and I estimate that it's a control room because there is what appears to be an engine telegraph here on the right hand side, and below that there are what appear to be twin throttles, which would be for the twin turbines which are connected to the single screw. I'm not 100% on that. I got this picture from the internet. So if any of my viewers knows, and as ever, if any of my viewers wishes to put any corrections or comments, then please feel free to fire them down in the box below. With that in mind, let's get started. The first thing I want to talk about is the roles of nuclear submarines. Here on the right here we have a picture of a British Trafalgar class submarine, and it's being visited by an EH-101 Merlin helicopter. Now, I mentioned the Merlin helicopter in my Type 23 presentation. It's a very effective helicopter. This was probably during some kind of anti-submarine exercise. On the left here we actually have a picture of a United States Ohio class submarine. This is a missile submarine, and we see here with the missile tubes open. Now, all submarines that are powered by nuclear propulsion systems are designed exclusively for warfare. Now, this is a shame, I will admit. It is not really where I would like us to be as a civilization, but the reality is that nuclear propulsion systems are so complex and so expensive that they really serve no useful or practical civilian purpose. So every submarine in the world that has a nuclear reactor is designed for one thing, and that is to kill people ultimately. That is a shame, but it is the way it is. There are, generally speaking, two classes of submarines. So we have attack submarines and strategic missile submarines, and we'll look at them in a bit more detail over the next couple of slides. There is a third kind of class of submarine, which is the cruise missile submarine, or which sort of falls in between the other two, but they're not that common, and I would class them more towards an attack submarine. All countries with their own nuclear submarines currently operate both types. Now, I put a caveat on their own nuclear submarines for the reason that India currently leases a couple of attack submarines from India and does not, as far as I know, or as far as most people know, operate ballistic missile strategic type submarines. Missile submarines could not really exist without nuclear power, and we will see why in the next slide. So missile submarines only really were developed following the deployment of nuclear power to submarines in the early 1960s. Before that, there had been considerations of them. The Germans, for example, had various harebrained plans to mount V2 rockets on U-boats, but they wouldn't really have been that practical. In many cases, the V2 rocket wasn't particularly practical in the first place, as I mentioned in my introduction to rocketry lecture. And attack submarines do exist without nuclear power and have a long history. As you know, the first and second Battle of the Atlantics were fought exclusively with non-nuclear submarines because nuclear power didn't exist then, and they are still made today, but I've put here that they would be significantly less effective without nuclear power. So they're non-nuclear attack submarines are generally not effective on the open ocean. They're too slow and they have a constrained underwater performance. They do, however, have a role to play in the littoral where they can be very quiet. In general, I have a slightly cynical view on what we call conventional, that is non-nuclear attack submarines, which is there is a lot of talk about how incredibly quiet and difficult to detect they are, and that may well be the case, but in the open ocean they will be detected relatively quickly. They will be blown out of the water relatively quickly because they simply don't have the underwater range or underwater speed to evade something that can travel at 30 knots and has the ability to use active sonar because it knows you can't hit it. So other than sort of inshore areas, I would say a non-nuclear attack submarine isn't going to get you very much. They are operated by a lot of countries which have very shallow littoral conditions, such as the Netherlands, Sweden, Germany, and so on. But I suspect if it was up to any of those countries, they would, in addition, operate nuclear power submarines. But for various reasons, they cannot and do not. Let's look first at the role of the missile submarine. On the left here, we have some diagrams of the main classes of missile submarines that are operated in the world today. Now, they are operated by the big five nuclear powers, which are obviously the United States of America, China, France, the United Kingdom, and Russia. Now, Russia has several types of missile submarine in operation today, and it is possible that China does as well. The United Kingdom, France, and as far as I know, the United States currently only operate one type of missile submarine, which in the case of America is the Ohio class. In the case of France is the Triumphant class. You'll have to excuse my pronunciation there. And in the case of the UK is the Vanguard or V-class boats. Now, they're all quite large. In the case of the Ohio class, they're pushing 19,000 tons displacement. Even the British Vanguard class is 16,000 tons. Now, there are similarities between the Vanguard class and the Ohio class, and the similarities are that they carry the same missile, albeit the Vanguard class carries 16 Trident missiles and the Ohio carries 24. All the other types of submarines carry their own missiles. So missile submarines are a single role submarine. Their role is to launch nuclear tipped intercontinental ballistic missiles. That is a deeply morally questionable role, but it is the role that they exist for. And in this talk, I'm not necessarily going to get involved in the moral side of it. For the record, I do not like them, but that is not what I'm going to talk about today. They primarily, in order to achieve that role, they sort of hide, as they say, often with pride, and the designs are optimized for stealth above pretty much everything else, including living conditions. Now, what that means is that these things take no chances at all. Once they leave the port, they go off somewhere. Only a handful of people will know where they're going, and only a handful of people on board will know where they are. So the majority of the crew, for example, will not know the location of the missile submarine at all. Only the navigator, the CO, and a handful of others would be party to that information. They will go off for a patrol for a number of months, and then they will return, and during that time their main focus is not being detected, because if they are detected they can be killed, and they will not get a chance to launch these missiles if they are detected. It's highly likely that if they ever did launch these missiles, that they would be blown out of the water with quite an astonishing degree of rapidity, because if you detect nuclear missiles taking off, it's relatively straightforward with radar to detect a ballistic course from whence they came and lob another ballistic missile at the general launch area, which, if it's nuclear powered, or rather nuclear tipped, excuse me, will blow up the launch submarine. They are, because of this role of launching ICBMs, probably the most secret assets that any navy has, and they're generally bigger and much more expensive than attack submarines. And a lot of that expense comes from the need to maintain stealth at all costs, the need to maintain these things in absolutely pristine, tip-top condition, the need to train people to operate them rigorously, and the need perhaps to maintain this continuous at-sea deterrence. So in all of these countries that operate these submarines, they will all take pride in the fact that at least one of them, or in the case of the big boys like America and Russia, several of them are at sea at one point, ready to launch. The UK, for example, has had at least one at sea since the mid-1960s, and they take a lot of pride in that. I guess it's something to be proud of if you measure your pride by that ability, but what it means is that it's very expensive to achieve that. You can't cut corners. So let's look at attack submarines now. This is a view from a helicopter of a Royal Navy Trafalgar class attack submarine, which is a very successful submarine operated in the Royal Navy from the 1980s till today. Several of them are still operating. Attack submarines are multi-role, so they have a lot of different jobs to do, and they tend to be smaller, they're a lot cheaper, and they are also relatively quiet. Some of the roles they do is anti-submarine, obviously, so one of the best ways to find a submarine is by looking for it with AN other submarines. So attack submarines will be tasked to search for, and if necessary, destroy missile submarines. Anti-surface ship, yes, they can be operated in that role, and in particular the Russians like to use submarines in that role, particularly for searching for things like United States aircraft carriers. Shore bombardment is exactly what it sounds. So a lot of attack submarines will have cruise missiles fitted, so most Royal Navy submarines have that, and as I mentioned earlier, there are some specifically dedicated cruise missile submarines, which I would also call attack submarines, which are fitted with a larger number of cruise missiles. But the advantage is that you can quietly approach a shore and launch a cruise missile relatively undetected and unbothered. For the same reason that they're quiet, you can do intelligence gathering from them. So that could involve any number of things. It could involve parking yourself off somebody's shore and listening acoustically, listening electronically with for radio signals, for example. It could involve placing special equipment on the seafloor or the hulls of other vessels. It could involve launching divers and so on and so forth. So from an intelligence gathering point of view, these things are very useful. And that flows into special operations, which is what you might want to do once you've gathered a significant amount of evidence. So some of these attack submarines can have launch and recovery systems fitted for special underwater operations, for miniature submarines, and so on and so forth. So the attack submarine is a really versatile unit that is tasked to do a lot of things, and they can do a lot of things, and they are a very potent weapons system. Personally, if I had the choice of having either a ballistic missile submarine or an attack submarine, I would want attack submarines in my navy because they are actually used to do useful stuff on a daily basis. As I said, there's no navy that only operates their own attack nuclear submarines except India, but as I don't really class them as operating their own submarines because they're on lease from Russia. For this presentation, we'll mainly be considering a quote-unquote typical Western attack submarine. I'm essentially going to base this talk on the Royal Navy Swiftsure / Trafalgar class of submarines as a general introduction, as they are fairly representative of a good, modern, successful attack submarine. I just want to make a quick observation on size of submarines. Now, submarines have a reputation for being cramped, as we know. Now, if we look at the table on the right here, we've got a Type 23 frigate and a Swiftsure class submarine. Now, a Swiftsure and a Trafalgar are similar. I know this silhouette here is of a Trafalgar and not a Swiftsure, but bear with me anyway. So, as we can see, they both displace the same amount, 4,900 tons for the Type 23 frigate and 4,900 tons for a submerged Swiftsure class submarine. But if we look at the lengths, we've got 133 meters for the frigate and almost 50, well, more than 50 meters less, 82.9 meters for the submarine. Got a beam of 16.1 for the frigate and only 9.8 for the submarine. We've also got a higher crew complement on the frigate, but still we can see that with these dimensions, there's going to be a lot less room per person on the submarine. Now, the Type 23 and the Swiftsure have the same displacement. The volume, however, of the submarine will only be equal to the submerged volume of the Type 23. Hence, for a given displacement, i.e. in this case about 4,900 tons, a submarine will have significantly less room than a ship. You can see what I mean here. A submarine is under the water. That means that when it's displacing 4,900 tons, its entire volume cannot be more than that. Whereas a frigate, most of it is outside of the water. The part that's underneath the water is displacing 4,900 tons, but it has maybe 2 or 3 times as much volume again above the water. So although a submarine and a frigate on paper may weigh the same, and they do, they are physically made out of the same mass of steel, the surface ship will always have 2 or 3 times more internal volume, and that is why a submarine is cramped, even if on paper it has a large displacement comparable to a frigate and a lower crew count. For the same reason that the submarine will be more cramped than the equivalent surface ship, they will also have very little reserve buoyancy when surfaced and none at all when they are submerged. Now, what I mean by that is the amount of the difference, if I draw in the right here, between when a submarine is surfaced, it will actually only pop out a little bit above the water, as we've seen in the preceding photograph. So it'll pop out by the amount that I'm cross-hatching in red here. Now, as I mentioned with the surface ship, most of it is above the water, possibly 66% volume will be above the water and 33 below. Now that means that it'll have a reserve buoyancy of double the submerged. So in that instance, it would have a reserve buoyancy of 200%. Now it doesn't, because once you get slightly down the hull, you will start having openings, and of course if the waterline was above the hull, then it would just ruin the ship and go in through all the vents. So in actual fact, the Type 23 might have a reserve buoyancy of something like 100%, whereas a submarine will have a reserve buoyancy of between 10 and 25%. In addition, I put that neutral buoyancy is difficult to achieve in practice, so most submarines operate slightly heavy and use the bow planes to fly. We'll look at that more in part 2, but what I mean is that when you have water, and if we have the sea surface here, I will indicate that it's a sea surface by putting a little boat on it. Underneath the water we might have a submarine, and the submarine will be trundling along quite happily. But water, although water is incompressible and a submarine is made out of metal which doesn't compress that much, because the pressure rises as you go down, it rises by 1 bar per 10 meters of depth, then that will squeeze the submarine a little bit and it will compress it a little bit, and that will mean that the submarine displaces less, which means it sinks more and so forth. So you actually get positive feedback. To get absolutely neutral buoyancy, as in if you stopped the submarine, to have it in a position where it would neither go up nor down of its own accord is incredibly difficult to achieve, not just because of the compressing of the submarine itself, which isn't particularly significant, but because of the change in the number of fluids that are inside the submarine. So there are various seawater systems that go into it for cooling purposes. They may change. You might have a different amount of food on board from where you started, that you might have emptied the sewage, for example, or launched a torpedo. So in practice, it's almost impossible to achieve neutral buoyancy, and if you do, it'll only be for a short amount of time. So what the majority of submarines do is move, and they will use the control surfaces to maintain a given depth. Generally they operate slightly heavy, so when I say slightly, that is several tons heavy. So it's not you can tap it with your finger and it'll go up or down. It's maybe a double-decker bus too heavy, and that's typically how they operate. It is a concern that you have to deal with when you're in the business of operating a submarine. Okay, let's look now at some of the characteristics of submarine propulsion. Here we have a Royal Navy Vanguard class submarine, again leaving my doorstep of Faslane. It's a really quite steely photo, this, with the snow in the background and obviously a very low sun. Believe it or not, back in the day, submarines used to enter and leave Faslane totally submerged, and that was a pretty ballsy call, as it's a relatively narrow channel, but these guys used to know what they were doing, and I think they still would be capable of doing that, but various safety regulations, etc., mean that, as far as I know, they don't. It may be that they do, because of course if they're submerged I wouldn't see them. So key characteristics of a submarine propulsion system include, and this is I think the most important, no requirement for oxygen, and can therefore operate submerged for a very long period of time. Now that to me I think is probably the most important characteristic of a submarine propulsion system. So before the advent of nuclear power, this was not possible. So if you were operating on diesel engines, you needed a snorkel, and if you were operating on batteries, the batteries would run out. But that is not a problem with nuclear propulsion. Nuclear propulsion does not require oxygen, and it can therefore operate forever. And that ability meant that it was then suddenly possible to put much more powerful plants into submarines. There's no requirement for frequent refueling, and by frequent refueling I mean refueling every few days or every few weeks or even every month or two. The fuel lasts for years. Now, how long it lasts depends on a lot of things, including what type of fuel you've got loaded, the design of the reactor, how the submarine has been operated, and what you mean by last. But don't worry, we'll talk about that in part 2, as it's quite an interesting subject. There are no emissions of smoke. Now, as well as having a nice environmental benefit, it does have the rather practical benefit that it can't be seen at long range, particularly during World War I, when there were still a lot of coal-powered ships. Ships were detected at vast range from the smoke from their funnels. That was a key driver in transferring a lot of those ships to oil firing in the interwar years, and that became a lot more difficult to do in the Second World War, but it was still done and is still done today. It's also done with infrared, of course, today. Now, a submarine does not leave a trail of hot smoke wherever it goes, and therefore that's not going to be able to be detected by anything. Detecting a submerged submarine is relatively difficult unless you are fairly close to it. Now, obviously that's all wonderful, but if it was truly wonderful, everyone would have them, and they don't. So why not? Well, The first and probably biggest problem with nuclear propulsion systems is their extreme cost. So billions and billions and billions and billions per unit. Now, if I can go off on a side here, there is a lot of nonsense being talked at the moment about a thing called a SMR. So I'm going to write that down. Now, an SMR stands for Small Modular Reactor. I promise this is going somewhere. Now, every nuclear manufacturing company, including Rolls-Royce, is banging the drum of SMRs at the moment and saying that these magical reactors will be somehow cheap and effective and we can just throw them everywhere. And one of the things that they're saying is that because they're small, we can make them in factories and they will be cheap. But you know what? Submarine reactors are small and they're made in factories and they are not cheap. And I will go probably on a rant about SMRs and the utter absurdity that is the SMR concept, perhaps in another presentation, but I just thought I'd mention it as an aside here in case you want to go and research it for yourself. They are not inherently quiet. Extensive silencing measures are needed. Now, as I mentioned in a Type 23 presentation, submarines and anti-submarine equipment needs to be quiet. So sound travels very well through the water. It travels much faster through the water than it does through the air, and it attenuates a lot less through the water than it does in the air. And that's why marine mammals know a hell of a lot more about sonar than we do and have been using sonar for millions and millions of years. And it's also one of the reasons why marine mammals do not like it when we start putting noisy ships and submarines in their water. Now, if you don't want to be detected in a submarine and you want to detect somebody else, then you need to be as quiet as possible. And there is nothing inherently quiet about a nuclear power system, unlike a battery with an electric motor, which is inherently quite quiet. So to make a quiet nuclear submarine requires a lot of quite expensive and complex engineering. It requires highly trained, competent and expensive operators and support staff. I'm sort of sticking in my throat a bit when I have to call submariners that, but yes, submariners, or at least submariners who operate nuclear plant, they really are very good. They, you know, it hurts me to say it, but they're good. They're very well trained, they're very competent, and as a result of that, they cost quite a bit of money. They get submarine pay in the UK at least, which amounts to a significant amount. And of course, if they're on patrol, they don't have a great deal to spend their money on, so when they come back they have a big fat wedge, but in my mind they earn a lot of it, so I don't have a problem with that. They require considerable shore civil nuclear infrastructure. So when I say shore civil nuclear infrastructure, I don't mean the base from which to operate the submarine from, although that is also a key piece of expensive infrastructure. I mean the infrastructure to make the fuel that goes into the submarines, the infrastructure to build the submarine components, the infrastructure to train people to operate the submarines in a safe way and test the developed reactors. And of course, what we don't have in the UK, the infrastructure to get rid of the damn thing once you've finished with it. Hence disposal and waste issues. Now, what we like to do in the UK when we've finished with nuclear stuff is park it somewhere and leave it there for a long time so that we can get around to it at some distant point in the future. If it's civil nuclear waste, we sometimes get as far as encasing it in concrete or at least throwing it into a big swimming pool where birds like to nest because it's nice and warm. But what we have not done is got rid of a single nuclear reactor that we've ever built on a permanent basis. Certainly not for submarines, which is why there's so many used nuclear submarines laid up in Plymouth. And of course, it goes without saying that they are hazardous in a faulted or a war damaged state. Now, generally speaking, if you're at war and you're in the process of blowing up nuclear submarines, things are going to get very bad very quickly, and you will probably end up having bigger problems than a relatively small nuclear reactor in pieces at the bottom of the sea. Nonetheless, that is a real concern, particularly if it happens in the littoral. Now, nuclear submarines have been lost. The Americans have lost 2 and the Russians have lost considerably more than 2, often in quite amusing circumstances. And so there are a worrying amount of nuclear reactors sitting around at the bottom of the sea already. Then finally, we have the political and public perceptions, pressure and interest, and that, along with the cost, is probably one of the main reasons why nuclear submarines have not been more widely adopted. There's plenty of countries in the world, Sweden, for example, Canada, Germany, which definitely have the capability of designing and building these things, but they haven't. And many of those countries have expressed interest in it in the past, and they've hit issues generally political within their own country. A lot of the time, I think people don't necessarily understand the fundamental difference between a missile submarine like this Vanguard class and an attack submarine. So obviously, if you're building missile submarines, that is very easy to see the bad side of that. But a nuclear attack submarine is actually a very useful part of any blue water navy, and I am quite surprised that Canada, for example, has not got its own nuclear attack submarines, or Japan would be another one that I think would benefit significantly from that capability, as would Australia. Okay, there are two types of nuclear propulsion system that have been deployed on submarines. Now, I'm not going to go into the detail of them in part one, but I will very briefly explain what they are. By far, the most common submarine reactor is the pressurized water reactor. In fact, it's not only the most common submarine reactor, it is the most common civilian reactor as well. There is a reason for that. It was adopted for civilian purposes, having been developed originally in the United States for submarines. Now, from a civilian point of view, I don't actually like pressurized water reactors. I do not think they are a particularly good reactor for civilian use, but they have a very useful characteristic for submarine use, and that is that they are compact and they can be shoved into a very small place. It consists of a nuclear kettle at the center, which heats up water and does not boil it. And that is the primary point of a pressurized water reactor. Because it doesn't boil it, the pressure raises. It pumps that water throughout steam generators and back to the reactor pressure vessel. And the steam generators, they interact with a secondary system which goes through the steam generator but doesn't mix with the reactor water, and that flashes off to steam. But we'll look in that more detail in part two. The second type, which has some significant advantages but is also complex and have only been deployed in a handful of submarines, is the liquid metal cooled reactor. Now, the second ever nuclear submarine, which was the USS Seawolf, had an experimental liquid metal cooled reactor. In addition, the Soviet Union put the Alpha class submarines into production, which also used liquid metal, and the Alpha class were the fastest and most deep diving submarines ever to enter service, although they were very noisy. Liquid metal has some significant advantages. However, it also has big disadvantages. The most obvious problem with a liquid metal cooled reactor is that when you shut it down, the metal will solidify and you will never get it going again. Now, different types of metal cooled reactor have used different coolant. Generally speaking, the Americans and most countries that have been developing fast breeder reactors have used sodium as a coolant. Sodium, of course, reacts extremely violently with water, and therefore that's another safety issue. But the Alpha classes used a eutectic mixture of lead and bismuth, which melted in the sort of below 200 degrees. I can't remember off the top of my head. I want to say 152 degrees, but that sounds a little bit low. And that was a relatively successful approach, but nonetheless, as far as I know, most of them froze, and they would have had to have been hooked up to special source steam supplies when alongside, or they would have to keep the reactor running at all times, and you really wouldn't get much of a chance to shut them down for repairs. So for that reason, liquid metal cooled reactors have not seen widespread use, although there are significant advantages to them. And that is also the case on the civilian side of things, where there have been several liquid metal reactors built. In the UK, for example, we had 2 fast breeder units up at Dounreay in Scotland, and they operated relatively successfully, but nonetheless they are a difficult technology to master, and because PWRs are so much more straightforward, they are by far the most common type that we see. The reactor essentially generates heat. Now, almost every nuclear submarine in existence will use one of the 2 types of propulsion system that we're seeing here. Neither of these is the fictional magneto-hydrodynamic drive that we saw in the Hunt for Red October. I'm not ruling out those existing, hence why I said almost every submarine. However, every submarine that I know of operates on one of these 2 systems, which are the steam turbine plus gearbox, which is by far the most common system, and on the right here the steam turbine plus generator plus electric motor system, which tends to be played with every few years as propulsion motor development improves. So USS Tullibee, which was launched in 1960, had this system with the generators and the propulsion motor. They tried again about 10 years later with the USS Gerard P. Lipscomb, I believe it was called. The French used them, as far as I know, on their ballistic missile submarines, and it's possible that other submarines that I don't know about have deployed this type of propulsion system. However, by far the most common is the type we see on the left. So what you have here is a nuclear reactor which creates a hot place inside the steam generators, and then we pump water into loops within the steam generators. That water flashes off to steam, and then we have essentially a quote-unquote conventional steam plant system. Now, anyone who says conventional steam plant probably doesn't know much about steam plants. Steam ships in particular are very complicated things. I have not operated them, and it is difficult to find many people who have, who are not submariners. But steam ships are complex, and you really have to know what you're doing with them. So it's not as straightforward as we pump steam into the turbine spins, and then we condense the water and it goes round in a big loop. That is essentially what happens, but you have an awful lot of support systems doing that. On the gearbox type system, generally there will be more than 1 turbine, and generally there will actually be 4 turbines, 2 to go ahead and 2 to go astern. And in this system here, which we'll look at in more detail later in this presentation, that will go through clutches, through the gearbox and to a propeller. With the steam turbine electric system on the right, this is not a particularly new system. There were battleships launched in America in the 1920s that had this system, but nowadays with advanced induction motors and conversion machinery, it is more practical to do this in a compact, quiet and efficient manner. What you'll have is a very similar system where the steam turbines will be connected to generators, and those generators will provide electricity to a switchboard and control system, which will provide energy to a propulsion motor, which will drive a propeller. Now, there are numerous advantages to this layout, which should be fairly self-evident. For example, we don't need reversing turbines. We don't need a reversing gearbox, and we can in principle shut the reactor down completely and operate very, very quietly on battery control. Disadvantages though tend to be that these systems, until recently at least, have tended to be a bit more bulky and a bit more difficult to shoehorn into an already confined space that is a submarine. So most submarines are single screw, and most will have emergency retractable electric thrusters in addition to the single screw drive. In addition, what we will see later is that even submarines that operate with a steam turbine gearbox and propulsion configuration will always have, or usually have, an additional electric motor coupled into the gearbox side of things, and we'll have a look at that later. So in general, most submarines operate the system used on the left. Some submarines operate the system used on the right, and I would expect that due to advances in permanent magnet motors and power conversion equipment and batteries, that more and more submarines will adopt the situation that is on the right. Also bear in mind that quote unquote conventional, i.e. diesel electric submarines, will almost always use a system similar to the one on the right, except that the diesels will drive the generators instead of the steam turbines, and there will be no mechanical connection between the diesel engine and the propeller. Once we've got something spinning, we then need to make the submarine go through the water, and again there's two main types of propulsor, i.e. two main types of forcing the submarine through the water. What we see here on the left is a propeller type. So this is a high skew, odd bladed, low cavitation propeller. This is a picture off the internet. I believe it's on a conventional diesel electric submarine, because propellers are highly secretive things, and there definitely is not just going to be casually a picture of a propulsion system of a nuclear submarine floating around the internet. So most American submarines and most Soviet submarines have tended to use a propeller. Now, why does it use an odd blade? Well, it's quite simple. If we look at the back of a submarine, generally they have an even number of control surfaces, so they'll have a sort of cruciform shaped control surface. In order to avoid interference and regular beating with that control surface, which we'll see here, so it'll be on the left, I'm just sort of drawing in red across, then we use an odd number of blades, because otherwise you would get a regular interference pattern between the rotating propeller and the control surfaces. The skew is there for a similar reason, that as that propeller crosses the control surface, it doesn't cross the entire control surface at once. It does it on a sort of sliding scale, and that tends to reduce the amount of interference and therefore noise that you're getting as that propeller crosses the turbulence that comes off the back of the control surface. Now, bear in mind, of course, that both of those features may well lead to a less efficient propeller, and their performance in the astern mode may well be severely limited, but that is a price that is worth paying in order to achieve a low degree of noise. Now, it is possible that these things get dented or dinged or hit other ships or submarines or whales or whatever, in which case you will tend to get like a little bend on a propeller, and therefore it is possible to identify submarines from that acoustic signature of a slightly bent propeller blade or a slight amount of weed or whatever. Every submarine will have their own acoustic signature, and as long as you know what you're listening for, then you can save that characteristic and know it again. Now, on the right we see the second type of propulsion system. This is the shrouded pump jet. So most British submarines, including all but one of the Swiftsure class, which came out in the 70s, and all but one of the Trafalgar class, which came out in the 80s, and all of the Astute class and all of the Vanguard class, use a shrouded pump jet design. As far as I know, the Royal Navy were the first to deploy it, but I could be very wrong on that. Modern French submarines also use it, as do the newer US and Russian designs. Now, you will not really find a picture of a pump jet of how it works. This submarine here, you will note, has a shrouded pump jet, but it's covered in plastic. And that's to prevent anybody from photographing the inside of it, even a satellite potentially. Now, essentially all that you have in there is a shrouded propeller, but the actual mechanics of how it's organized, what skews it has, the combination of rotors and stators, whether it's single rotating or contra rotating, all of that is not the sort of thing that's in the public domain, and it is not the sort of thing that I would talk about. It is just worth knowing that they're there. In general, they are quieter than a propeller, and that is generally why they are increasingly adopted, but they are also more difficult to design, and that is why they were not more widely adopted until recently. As far as I know, that's also why the first-in-class Trafalgar and the first-in-class Swiftsure had conventional, well, semi-conventional propellers instead of pump jets. I believe that was to get a feel for how the submarines would operate in case the pump jet didn't work, but again, I'll stand corrected on that. Nowadays we don't tend to launch the first of class submarine with a propeller instead of a pump jet, presumably because our numerical models are better and we've got a better understanding of how these things operate. Okay, let's look now in the briefest terms at some typical noise reducing features that we might see on a submarine. Here's a Soviet, I believe, Akuda class attack submarine. It was a pretty cool photograph, so I thought I'd put it there. So we raft the machinery to make sure that, as far as possible, any noisy equipment is not rigidly connected to the submarine's hull, and that really will significantly minimize the transmission of noise to the hull and the outside sea. We'll probably be using special gear tooth profiles on our gearboxes, so our gearboxes will definitely be helical for noise reduction and possibly double helical, and may have non-involute profiles, which probably would result in slightly lower efficiency. Obviously, because the gearbox is going to be on a raft and that raft is going to move relative to the hull, we're going to need some kind of flexible drive shaft to transfer the torque from the gearbox to the submarine's propulsor. And speaking of propulsors, we're going to have some kind of low noise optimized propulsor, which again might be slightly less efficient than a typical propeller, but will be less noisy. Wherever possible, we're going to try and operate our machinery in the low power state. Now, obviously, that's only possible if we're traveling slowly. Traveling fast on a submarine is going to be inherently significantly noisier than traveling slowly. If one travels very, very slowly in a submarine, and by that I mean something like 5 knots, then it will be very, very difficult to detect that submarine, because in the book it will say what machinery is to be operated in which power state. So the lower power states require significantly less ancillary machinery as well as main machinery. Generally, there's going to be acoustic hull insulation tiles fitted. Now, we've seen them in a few pictures. Generally speaking, they're the things that drop off during a patrol. So when a submarine comes back, you see little patches of rust underneath the black acoustic tiling. I did a little bit of research onto these, and actually they were first developed in Germany in the Second World War, and then for whatever reason fell out of favour for a couple of decades after that before being rediscovered. They may be fitted with laminar flow design pipework. In other words, there'll be cascade features in certain pipework, and there will be an emphasis on fewer big right angle bends. And of course, they'll have self-diagnosis in the form of hull vibration and monitoring systems. So these are going to be able to detect what noise the submarine is making and allow the engineers on board to isolate any faults and correct them. In addition, there will be noise ranging trials done on all new submarines and submarines out of refit, where they'll essentially steam up and down in a known place in known machinery states, whilst special external equipment is used to monitor their noise performance. Very important, we have crew training and discipline. So all of this equipment can be very good, but if it's not maintained properly, and if more crucially it's not operated properly, then it is going to be noisier than if it's operated correctly. In addition, just normal activities of the crew, stomping about the ship, banging things together, cooking, etc., may result in enough noise that it is detectable to other submarines. So there's a certain amount of discipline that's going to have to be required from that crew, and a more disciplined crew is going to be a quieter crew. As I said, the most effective noise reduction method is simply to move slowly or not at all. And without effective maintenance, submarines will become noisier as they age. So not only will newer submarines be developed with a lower noise signature, but submarines that are in service will tend to get slightly noisier the older they get as they wear out, and it's uneconomic to necessarily replace every single component on them and every single bearing and so forth. So that is one reason why submarines may be decommissioned, even if their material state is not that bad. Well, so much for that. Let's now look at a summary of what we've learned in part 1. So nuclear propulsion has given submarines tremendous capabilities in terms of underwater performance, range and speed. And it really has, and it's done that for 5 decades now. There is nothing on the drawing board at the moment that has any possibility of replacing nuclear power in terms of those capabilities. Even very advanced battery systems are not really going to be in a position to alter the strategic balance in that regard. But the systems are complex and extremely expensive. Most submarines in service today rely on a pressurized water reactor coupled to a propeller via a steam turbine and a gearbox. Now, there are other configurations which are in service and other configurations which have been tried, but the majority have adopted this solution. As the systems, and by that I mean nuclear power and its associated clunknudgery, are not inherently quiet, special measures have to be designed to reduce the noise signature, and that can result in some fairly extreme engineering with the resulting high associated costs. Now, in part 2, we're going to look in more detail at the operating characteristics of a pressurized water reactor. We'll look at the need for and methods of generating and handling electricity, and we'll introduce supporting systems such as forced lubrication and air, and I hope you'll join me for that. Just before we go, here's a picture on the left of a Los Angeles class submarine, American attack submarine, and they're obviously conducting some kind of helicopter operation. You can see this crew member here has a yellow stick with a hook at the end, and what that is an earthing stick. So the other end of that stick, the end that you can't see, will be connected via a flexible lead to the submarine's hull. The helicopter will be dangling a wire from its winch, and this crewman will attempt to hook that wire with the stick, which will therefore earth the helicopter, because helicopters can build up quite a big static charge when their rotors meet with moisture particles or dust particles in the air, and if you don't decharge it, you're liable to electrically shock yourself or worse when you come into contact with the helicopter. So again, thank you very much for your attention during this talk. I do hope you enjoyed it. If you've got any comments or indeed corrections, please feel free to put them in the box below, and I hope you'll join me for the next section. In the meantime, enjoy the rest of your day. Good luck.